Hi everyone, I'll be talking about prover-efficient public coin emulation of interactive proofs, and this is joint work with Guy Rothblum. An interactive proof is a protocol between a prover and a verifier, where the prover is unbounded and the verifier is computationally bounded. The prover is trying to convince the verifier that some instance X is in a language. We require that if the prover is telling the truth and X is indeed in L, then the verifier accepts with high probability. On the other hand, if the prover is lying and X is not in the language, then the verifier rejects with high probability, no matter what the prover does. And in this talk, we'll also be talking about a variant of interactive proofs known as doubly efficient interactive proof, in which the honest prover is required to run in polynomial time, but soundness still has to hold against unbounded provers. A private coin interactive proof is one where the verifier begins by choosing secret randomness, and then all of its messages can depend both on this randomness and on whatever it received from the prover. At the end of the protocol, it looks at the randomness, looks at the entire transcript, and decides whether to accept or reject. On the other hand, in a public coin proof, the verifier only sends uniform and independent randomness in every round. So why do we care about public coin proofs? Well, we know how to analyze them very well, so we can achieve a lot of different things with them. For example, we can achieve perfect completeness, that is, instead of the verifier accepting with high probability when X is in the language, it accepts with probability 1. We can reduce the number of rounds by a constant. We can make them non-interactive using the Fiat-Shamir heuristic. We can make them secure using zero knowledge. They also have a nice online-offline form in which while interacting with the prover, the verifier doesn't have to do any computation. It just needs to be able to generate randomness. And only afterwards, on an offline phase, when it doesn't talk to the prover, it can make its decision whether the claim was correct or not. So since public coin proofs are very nice, we'd like to transform any private coin proof into a public coin one. But we can do this. This was shown in the 80s by Goldwasser and Sipser. But unfortunately, this doesn't preserve the prover's running time, which is bad for doubly efficient interactive proofs where the honest prover needs to run in polynomial time. And we have strong evidence that this is inherent for any generic transformation. Specifically, Vadhan showed that assuming one-way functions, there exists a standard interactive proof, that is an interactive proof with an unbounded honest prover, with no black box transformation from private coin to public coin that preserves the prover's running time. And we actually show that this impossibility extends to doubly efficient interactive proofs where the honest prover does run in polynomial time. So even doubly efficient interactive proofs cannot be generically transformed to using public coins in a black box manner while preserving the prover's efficiency. In the rest of this work, we explore sufficient properties for efficient transformations. Specifically, our main result shows that efficient inversion suffices for this. Specifically, for every doubly efficient interactive proof, there exists an efficiently computable function such that if we can invert this function in the sense of one-way functions, then we can transform the proof into a public coin proof while adding only polynomial overhead to the prover's running time. And we can say something similar for any constant round interactive proof, even if the prover is not efficient. As a corollary, we show that in Pessyland, where one-way functions don't exist at all, if a language has a doubly efficient interactive proof, then it automatically has a public coin doubly efficient interactive proof. We also show another property, which is approximate counting. So if a language has an interactive proof where, given a prefix of the interaction between the verifier and the prover, one can approximate how many of the verifier's random coins are consistent with the messages that it sent during this interaction, then we can convert this language into a public coin interactive proof with similar prover complexity. Unfortunately, this transformation does not preserve the number of rounds, while the previous one does. We get out of these sufficient properties one application, which is taking the private coin doubly efficient interactive proof from Rothblum, Vadhan, Wigderson's work in which the prover proves to a sublinear verifier that some graph is close to bipartite. We managed to transform this private coin proof into a public coin one with roughly the same running time for the prover. So in order to show how inversion implies prover efficient emulation of interactive proofs, I'll start with a private coin protocol for graph non-isomorphism as an example. Graph non-isomorphism problem, you start with, you have two graphs, G0 and G1, and they're claimed to be non-isomorphic. And for simplicity, I'm going to assume that there are no non-trivial automorphisms. The protocol is very simple, it goes as follows. The verifier chooses one graph and chooses a random permutation, permutes the graph that it chose, sends that over to the prover. The prover needs to guess which graph was chosen by the verifier. The verifier accepts if the prover guessed the correct one. So notice that in completeness, if the graphs are indeed non-isomorphic, then G tilde has 2 times n factorial options because each isomorphism set of each of the graphs are distinct, and these are all the 2 times n factorial options. On the other hand, if they are isomorphic, there's only one isomorphism set, there's only n factorial options for G tilde. So the idea that Goldwasser and Sipser had was to use a set lower bound protocol to prove that G tilde has many options. How does the set lower bound protocol look? Well, we have some set that we're trying to prove that is large. Let's assume for now that we have efficient membership for this test, for this set. This set in our case was the number of options for G tilde. And we have a claim n, which is the size of the set. In our case, it was 2 times n factorial. The set lower bound protocol works as follows. The verifier chooses a hash function, pairwise independent hash function, and some image of a function. And the prover has to return some instance in the set that hashes to y, to the image. And the intuition, at least, behind what's going on here is that in the case of completeness, if the set is very large, and the hash function is compressing enough, then with high probability, every one of the bins, including y, will have some pre-image, it will have some instance in the set. So the prover will be able to return this. On the other hand, if the set is very small with respect to n, and the hash function is not compressing, is not very compressing with respect to the size of the set, then with high probability, most of the images y will not have some x and s that hash to y. So how is the public coin proof for graph non-isomorphism going to look? Well, the verifier chooses a hash function and an image y, sends that over to the prover. The prover now needs to return some G tilde, such that G tilde hashes to y and is isomorphic to either G0 or to G1. Of course, the verifier can't verify by itself that G tilde is isomorphic to either of the graphs, but this can be easily given to it by the prover, just tells it which graph and gives it an isomorphism between G tilde and the graph. So we're interested in the running time of the prover. So what does the prover actually have to do here? Well, it needs to find this B and this this permutation. It needs to find a permutation, a permuted graph for one of these two graphs that hashes to Y. And our observation is that given an inverter for this efficiently computable function that takes in a hash function, a bit choice of the graph, and a permutation, and outputs the hash and the hash applied to the permuted graph. If we have an efficient inverter for this function, then we'll be done. Why? Because these two, H and Y, are exactly images of what we need. If we had an inverter, a pre-image for H and Y would be some H prime, would just be the same H, and would be some B and pi such that H applied to the graph implied by G sub B permuted is exactly equal to Y. This is exactly what we needed. The prover can now compute G tilde and send over everything to the verifier, who can just verify everything. So what did we have here? For graphical isomorphism, we knew exactly the number of messages in completeness. We knew exactly the number of messages in soundness. All of the messages were equally likely because every graph in the isomorphism set was equally likely to appear. And there was only one round. It was a very simple protocol. In general, we don't know the number of verifier messages. Messages can have different probabilities, and general protocols have multiple rounds. So now let's look at a slightly more complicated protocol, which still has one round and perfect completeness, and all messages are still equally likely. But now we don't know the number of different messages that the verifier could send. So how does such a protocol look? So a protocol with L random bits and soundness S. The verifier begins by choosing its random bits. It then uses these bits to generate some message, receives some answer, some reply from the prover, and then uses all of these messages to decide whether to accept or reject. So notice that whenever X is in the language, if we look at the number of legal messages, a legal message is a message that has some randomness which explains it, that have accepting prover strategies. An accepting prover strategy is a prover message which causes the verifier to accept. So if we denote the number of messages by n, these are actually all of the messages because we assume perfect completeness. Then looking at a specific legal message, there exists a prover strategy for which the number of coins that lead to alpha, which explain alpha, and also cause the verifier to accept given beta, alpha, and rho, is 2 to the L divided by n. This is because all of the messages are equally likely, and so every legal message has exactly the same number of random coins leading to it, and all of them have some beta which cause them to accept for everything because completeness is 1. On the other hand, if X is not in the language, then this same set of legal messages when accepting prover strategy is smaller than S. S is the soundness times 2 to the L. This is because there can't be more accepting messages than there are coins which the verifier chooses such that the prover has an accepting strategy for them. And also, for every message alpha and prover message beta, the number of coins that are consistent with alpha and also cause the verifier to accept is also small. This is because, again, by soundness, the number of coins which the verifier chooses for which the prover has any accepting strategy is at most S times 2 to the L. So notice that in the case of completeness, either this value is large or this value is large. One of them must be large. While in soundness, they both must be small, assuming that S is small enough. So this gives us a strategy using the same set lower bound idea that we had before. The prover begins by sending a claim on the number of accepting legal messages. The verifier now wants to make sure that this claim is true. So they do a set lower bound protocol trying to prove this. Now this ends up, remember the set lower bound protocol ends with some claimed value in the set. And we have to check membership. So we get some alpha, some message that is claimed to be legal and claimed to be accepting. Remember, legal means that there's some randomness that explains it. So now the prover will send its own message in order to show that this is an accepting message. The alpha is an accepting message. And now they'll prove that the number of coins that lead alpha to accept, lead to alpha and verifier to accept given beta and alpha is large. It's 2 to the L divided by N. Remember, in the case of completeness, these two things are supposed to be true. This, and we end up after this with rho. And we have to make sure that rho is indeed in this set, but this set is easy to check membership for because we have everything. We just need to check that rho indeed leads to alpha and that the verifier accepts given everything it's been sent so far. So as I previously stated, for completeness, we already claimed that these are true. For soundness, we claimed that both of these sets must be quite small. And so due to the fact that either this claim is large or this claim is large, one of these claims will have to be small, will have to be a significant lie, and then we'll catch the prover in one of these set lower bound protocols if it's lying. So going back to what we're interested in is the prover's running time. So what does the prover have to do in this protocol? Well, it has to count the number of accepting legal messages in order to send it. And then it has to take its part in the set lower bound protocol for both the messages and the coins. So let's start with the first one. How can it know the number of messages? Well, we show that you can approximate the size of a set. This is in Pessyland when if you can invert a similar function to the one that we needed for the set lower bound protocol. And this is similar to something that Stockmeyer showed, but where he used an NP oracle, but it suffices to use an inversion oracle. Okay, so now let's go to the set lower bound protocol for messages. Well, we've already seen this. This is similar to graph non-isomorphism. We know that inverting a specific function specific efficient function will work for this. So, okay, let's go to the last one. Well, here something different happens. To see why, we're going to go back to the set lower bound protocol. In our case, the set are all of the coins that lead to some specific alpha, and the verifier accepts given these coins and the specific alpha and beta. The claim is, of course, that the set is large. I'll remind you how the set lower bound protocol works. The verifier chooses a random hash function, random image. The prover is supposed to send back something that is both hashes to y and is in the set in which the verifier can verify by testing that row indeed leads to alpha and causes the verifier to accept. So we want an efficient prover, and we want to do it in a similar way to what we did for graph-known isomorphism. The only difference here with that we have for graph-known isomorphism is that membership in the set is something non-trivial, and so we have to somehow make sure that the row that is given is consistent with everything here. So a way to do it would be to call an inverter for this efficient function f that takes in h and row and outputs h, the message implied by the randomness row and the hash of row. This is exactly what we need for the first two parts here. The last part we don't actually need because for the case of completeness, remember we're talking about the honest prover being efficient. In the case of completeness, every single one of the verifier's message randomness will cause the verifier to accept. So we don't really need to care about this last line. So why is an inverter for this function enough? Well, if we give it the hash function that we're talking about, alpha and y as the image, well, pre-image of these are exactly h and row such that v of row is alpha. So alpha is the message sent by the verifier given row, and y is the hash of row. It's exactly what we need. But now we run into a little problem because we want this inversion to be in the style of one-way functions. This means that we need that the images that are given are outputs of a random execution running the function on random inputs and uniformly random inputs. So this means that alpha has to be chosen from the correct distribution of a random row. And remember, alpha comes from the set lower bound protocol of before. That is, alpha was generated by this set lower bound protocol. So remember that in order to have an efficient prover, we gave the prover, the honest prover, an inverter for some function where alphas are the pre-images of this function. The problem with this is that usually when we think of inversion, we just think of returning some pre-image. And this would be problematic with the fact that we need alpha to come from the correct distribution. We would need alpha to be a random pre-image instead. So we can't use regular inversion. We can use a distributional inversion instead, which does exactly what I stated. It returns a pre-image that is uniformly random or close to uniformly random. And Pagazzo and Luby showed that if one-way functions don't exist, then anything can be distributionally inverted. So at least in Pesseland, we're fine. And we can also show that in general, there exists some function which, if we can invert it, then we're still fine. And once we replace the distributional inversion with the inverter with the distributional inverter, then we're fine. We're done. In the general case, that we still haven't dealt with, we have messages with varying likelihood. We have multiple rounds. We have imperfect completeness. All of these things have to be dealt with for general interactive proofs. And this is done in the paper. So if you're interested, see the paper for more details. As for open questions, we don't know many public coin protocols with efficient provers. We would want to have more. We also don't know the relationship between private coin and public coin for the efficient provers. As a concrete open problem, we ask, is there a public coin interactive proof for Graphanon isomorphism, where the prover is polynomial given access to a Graphanon isomorphism oracle. We know this is true for private coins. We don't know if this is true for public coins. Well, thank you for listening.